All right, chemistry, let's take a look at your review worksheet for the entirety of chapter 9. Number 1, given the following equation, we have a number of steps to go through. Start with A. What is the value of the coefficient x in this equation? Right, so that's this little guy right here. So essentially we're being asked what number can we plug in for x that will make this entire equation balanced. Now, first thing I want to point out is that you always have access to scratch paper. And the reason I bring this up is one suggestion that I always give, and I essentially beg my students to do that very few actually follow through on, is physically write down how many of each type of atom you have as you go along in this attempt to balance. Right? You don't want to try to remember these numbers in your head as you go, because all that does is detract from your mental capacity, right? Because you're going to have at least some amount of your brain power dedicated to remembering these numbers on the fly versus writing them down, not having to remember them, and then having the entirety of your brain power dedicated to actually figuring out the issue. Now, as we look at both sides of this equation, we actually see that the carbons are balanced. There are 3 on each side. We also see that the hydrogens are balanced. There are 4 on each side. But as I count the oxygens as they are, I see that there's 2 on the reactant side and 8 on the product side. So these oxygens are not balanced. So what can I do to that x? What number can I make this x? B, to make sure that the oxygens are balanced. Now, there's nothing I can do to this product side that will make the number of oxygens anything other than 8. So the question is, what can I put in front of this O2 to make the total number of oxygens on the reactant side 8? Well, that's a 4, right? Right? If I make that X a 4, I'll have 8 oxygens on both sides. B, what is the molar mass of C3H4? Now, this is a very fundamental process here in chapter 9. It's not the be all end all. You're not going to get a lot of points on a quiz for just being able to generate a molar mass. That's actually something that we did in chapter 3, but you have to use molar mass quite a bit. You're actually going to see that you're going to use molar mass here in part D. Now for carbon, there are 3 of them, and looking at your periodic table, you see that there's a mass of 12.01. For hydrogen, there are 4 of them, each at a mass of 1.01. Multiply those out. Add them together. 7, 0, that's 10, carry the 1. End up with 40.07. So the molar mass of C3H4 is 40.07. Molar mass is a quantity, which means it has a magnitude and a unit. So make sure you include that grams per mole. Part C. What is the mole ratio of O2 to H2O in the above equation? Now we just balance this, so it's a 4 to 2. So 4 moles O2 to 2 moles H2O. Now someone's going to say, hey, can't you reduce this to a 2 to 1 ratio? You sure can, right? That's totally okay. If you plug a 4 to 2 ratio into your factor label method of dimensional analysis, it will not affect your overall answer, right? So that's totally okay. I tend to shy away from that for 2 reasons. One, when I reduce these things down, that's another step. There's just a chance for me of doing something silly and making a mistake and getting the wrong answer. So I kind of tend to shy away from that. But also, when I work out problems, I like for students to be able to see exactly where I'm drawing the numbers from. And so I'm just going to keep that as the 4 and the 2, 4 and the 2. Now I'm going to use that molar mass I generated in part D. How many moles are in an 8.0 gram sample of H3SO4? Well, what's our given? 8.0 grams of C3H4. Now before I go any further, I want to point out that this has 2 significant figures. So I need to report my answer with 2 significant figures. Just keep that in mind as we go forward. I'm going to set up my crosshairs so I can do my factor label method of dimensional analysis. I'm trying to convert into moles, so that's definitely going to be on the numerator. Grams of C3H4 will be on the denominator, so that those units will cancel. And I pull the number that I generated for part B. And this tells me in order to get the answer that will actually get me points, I need to plug in 8.0 divided by 40.07. 0.199 blah 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 blah. I don't need any of this because I am supposed to report my answer with two significant figures, and so in order to report this with two significant figures, I'm going to round to that spot right there. The number behind that is a 9, telling me to round that up to the next, and that tells me to round that up. So the answer I'm actually going to report is 0.20 moles. In part E, if Z moles, just it's an unknown. If Z moles of C3H4 react, how many moles of CO2 are produced in terms of Z? Now we know that for every 1 mole of C3H4, right, C3H4 that reacts, we're going to generate 3 moles of CO2. It's a 1 to 3 ratio. You guys see that? It's a 1 to 3 ratio. For every 1 mole of C3H4 that react, we get 3 moles of CO2. If 2 moles of this reacted, we would get 6 moles of CO2. If 3 moles of this hydrocarbon reacted, we'd get 9 moles of CO2. But here we're being asked kind of a variable type question. If Z moles, well, it's 3 times however many moles of the hydrocarbon. So in terms of what I'm being posed here, I would get Z, right? In terms of Z, I would get 3 times Z. Whatever Z is, doesn't matter. It could be all kinds of different numbers. But whatever Z is, 3 times that number is the number of moles of CO2 that will be produced.